And I have quite a bunch of slides related to this topic, but I'll try to condense my message a bit. But to begin with, so there are different types of catalysts and catalysis, and also like in different fields. And the most common ones that we encounter in biofuel sector are heterogeneous catalysts and homogeneous ones. And there are also enzymatic catalysis and acid and base catalysis catalyzed reactions. The other photocatalysis, electro and organometallic catalysis is not really common in like biofuel production, but nevertheless, these are just like terms here to illustrate that catalysis can be found in various fields and connections. In the picture here, you'll see a kind of a heterogeneous, so that is, it's usually a solid catalytic material. So the active catalytic cycles take place on the surface of the catalyst. So the reactants dissociate, combine, and so on the surface. So these are like surface reactions. The upper right corner shows an enzyme. So that is typically a biocatalysis or enzyme catalysis, and also in biofuel production. So for example, fermentation of ethanol, fermentation of sugars, glucose to ethanol is one reaction where these enzymes are involved. Here, first I'll try to define catalyst shortly. I will not spend too much time on it, but here's the father of catalysis. So Swedish scientist Jöns Jakob Berzelius was the first one to define or started to talk about compounds that increase rate of reaction, and they are not like involved in the reaction, so in such a way that they are not consumed in the reaction. So those are neither reactants nor products. And that's the key in catalysis. So these are substances that increase rate of reactions that are thermodynamically feasible. And the reason behind this rate increase is alternative reaction path that catalyst provides that has a lower activation energy. So this little graph here describes the energy profile of a chemical reaction of one sort. So typically there is the starting energy level and the end level, and there this difference refers to thermodynamics. But then the energy barrier, the activation energy barrier, refers to activation energy, and that is proportional to rate of reaction. And without catalyst, it's in this case quite high, but when you introduce a catalyst, so there is an alternative reaction path which is illustrated with the dotted line, and it has notably lower activation energy, as you can see. And this is somehow how the catalyst rate increase is explained. So it will not influence the thermodynamic state. So the reactants gives energy and the products gives energy, or this E here can be whatever, but it only influences the activation energy barrier. Here is a similar, or not similar, but this is typical for homogeneous catalysis, or this type of profile where the even the catalyzed reaction has kind of a higher activation, like small positive activation energy barrier, so that it like this. This illustrates the activation energy of heterogeneous catalyzed reaction, and it's often so that you talk about the starting energy level. So the first step is there is no activation energy, so this is the adsorption, so it already jumps to lower level. But then when the actual reaction happens, so there is a tiny or larger activation energy barrier before for the formation of products, and those eventually desorb from the surface and form the product in the gas phase in this case. Here are a few points to keep in mind, and very relevant to industrial catalysis that we are like involved here in biofuels production. So the catalyst participates in the process in that change of activation energy, but according to the definition that it would remain unchanged, like that is not actually the case. The catalytic material, we'll take a look at later what materials typically exist, but these can change during the reaction or in a longer use. So it might not remain completely unchanged. So this phenomena is generally called catalyst deactivation. So there are certain changes that take place that lower the activity of the catalyst. Opposite to that could be catalyst reactivation, which would increase the activity. So these are kind of opposite phenomena, but the unwanted deactivation usually happens sooner or later. In some catalytic materials, it can take in few seconds, and in some catalytic materials in several years, or it takes several years to find a notable deactivation. But that depends case by case. Also, another thing to keep in mind is that chemical reactions like this thermodynamic state, it's defined basically based on equilibrium constant. So here is one example. So we have reactants and products, and this double-headed arrow is usually used in connection to equilibrium constant. This small k is rate constant. This upper one is forward reaction. The low one is backward reaction. And with the help of concentrations of these reactants and products, we can define equilibrium constant, which is equivalent to also to the rate constant. So equilibrium constant can be connected to the rate constants in this way. But the thing is that by introducing a catalyst, the thermodynamic state doesn't change. So basically this equilibrium constant remains unchanged. So that means that if the forward reaction is increased for rate, so also is the backward rate reaction rate increased. And this means that if we have like example, like we have a hydrogenation reaction and the opposite is dehydrogenation reaction. So if we want to find a catalyst for dehydrogenation and we don't know a good candidate, so we can also start to look for hydrogenation catalysts, because according to this basic definition, so the hydrogenation catalyst should accelerate dehydrogenation, and dehydrogenation catalyst should accelerate hydrogenation as well. So, but the thermodynamic equilibrium will not change. And actually, now that I see, I think there should not be a plus sign. This should be multiplied. So C times D divided by A times B. So reactions which are thermodynamically feasible, so that means that they have negative Gibbs free energy. So those are possible thermodynamically. So thermodynamics doesn't tell you how fast things are happening, because that is related to the activation energy. But if thermodynamics is telling that the reaction is not possible, so then no matter what catalyst you will choose, so it will not help the situation. So one has to be sure that it's thermodynamically sound and okay to carry out reactions, and then start to search for a suitable catalyst that would speed up the reaction so that it happens in a reasonable time. And this is quite often the case in this process development and particularly catalytic processes. So it can be, for example, calculated based on thermodynamic data, based on theory, that if certain reaction is possible or not. If you want to carry out that reaction, so you can try it in a lab scale first. And if the reaction is very slow, so basically nothing happens, so you have possibility to increase the temperature. And it's in most cases so that increase of temperature will increase the rate of the reaction. But it can still be that there is very little reaction happening in reasonable time. So then if you want to speed up things further, so you try to search for a suitable catalyst, and the catalyst can like speed up the reaction like 1,000 times or with the factor of 1 million. So it can influence quite a lot. So basically non-catalyzed, let's say that non-catalyzed reaction would take 2 years to go to complete conversion. So it can be that with help of a suitable catalyst that would take just 2 minutes. So it really has a notable effect on the rates of reactions. If it works okay, or if it's a good catalyst for that particular purposes. Homogeneous catalysis is defined so that the catalyst and the reactants are in the same phase. And very often when we talk about homogeneous catalysis, we are talking about reactions where we have liquid phase reactants, and also the catalytic material is in the liquid phase. In theory, there can be, or there are some examples that this homogeneous catalysis can take place in gas phase as well. And acid-base catalysis is typical example. This is, for example, in the hydrolysis of biomass. So acid catalysts will do the job. Also transesterification of triglycerides, making that fatty acid methyl ester, this biodiesel. So there one can use either acid or base catalyst, and that will speed up the reactions. In fermentation, in principle, if you have soluble catalyst, so one can also have homogeneous enzymatic catalysis. These are just certain examples. Heterogeneous catalysis is more common when we talk about fuel production and biofuel production. So there, by definition, the catalyst and the reactants are in a different phase, but again, it usually is understood in such a way that the catalyst is solid material and the reactants are gaseous, or reactants can be gaseous and or liquid. So this would be a three-phase reaction where there is a gas, liquid, and solid phase present. This would be a two-phase reaction with gas and solid. It's not usually when discussing heterogeneous catalysts, so that there would be gas and liquid. Although the definition is that it's in the different phase, but it's kind of normal, or it has been the approach that heterogeneous means more or less the same as a solid catalytic material. These are very common in industrial fuel production and in oil refinery and also petrochemical industry processes. So for example, hydrotreatments use solid catalytic materials. Many of these upgrading reactions of, for example, bio-oils that are made by pyrolysis. The Fischer-Tropsch chemistry runs on solid catalyst, and many more examples as well. This slightly grayish table so compares differences between homogeneous and heterogeneous catalysts and catalyses. And if you are interested, so you can perhaps study it in more detail. But in terms of reaction conditions, so the homogeneous catalysis is often applicable or functional at lower temperatures, whereas the heterogeneous, the solid catalysts work or function, or those can function at lower temperature, but the good thing is that they can tolerate very high temperatures up to, depending on the materials, but like 600-700 degrees at least is possible. Not with all, but some. I have later on a slide advertising or concluding some of the benefits of heterogeneous catalysis and why it's, let's say, the most popular choice for this large-scale fuel bulk chemical production. So catalysis is quite important, and one can summarize that there would not be any life on Earth without catalysis. So these enzymes that all living organisms contain, so make it possible that these metabolic reactions take place in our body temperatures, in very low temperatures, in controlled manner. So although we eat fuels, we eat fats and oils and carbohydrates, so those will not start to combust uncontrollably in our bodies and raise the temperature to hundreds of degrees Celsius. So everything is done at roughly 36, 37 degrees Celsius in a very, very controlled manner. And that is thanks to enzyme or biocatalysts that we have in all living organisms. Chemical industry is utilizing catalysis and catalyst, and it's very important in those areas. And although I said that heterogeneous catalysts are the most common ones in industrial scale operations, so there are examples of homogeneous and enzymatic catalysis also utilized in the industry. But if we think about the fuel production, so there are, I don't know, this number of 440 oil refineries worldwide. I don't remember which year, maybe 20 years ago. The number has probably decreased slightly. But in any case, so these are in this oil refining quite very important catalytic materials. Also, they can be used in pollution preventing and pollution abatement. So these end of pipe solutions, like we one week ago or something took a look at this air pollution, and for example, this diesel and gasoline driven car has catalytic converters to reduce emissions. So those are examples of heterogeneous catalysis or catalytic materials. Majority of industrial chemical processes, 80% based on certain sources, so are catalyzed reactions, catalyzed processes. And some 90% of commercially produced chemicals involve catalytic steps in their manufacturing process. So you can encounter these in various places when going to industrial commercial chemical production. Here are a few examples. So in petrochemical refining, so there is an alkylation reactions where you add alkyl groups into aromatics like benzene. So that can be done with zeolite. No, I think alkylation not so, but catalytic cracking is done with zeolite catalyst. You'll soon see what zeolites are. So they'll break the longer chain hydrocarbons into smaller pieces, and there are like hundreds of different zeolite structures and catalysts. Also, steam reforming, so making of synthesis gas. This is like similar, like what also is done in gasification of biomass. So we'll produce hydrogen and carbon monoxide. That's understood as synthesis gas. So that is done in the presence of heterogeneous catalysts. For example, nickel metal-based material works well. This we have already mentioned, and we study this in detail later. But one, like Fischer-Tropsch synthesis or Fischer-Tropsch reactions, are also catalyzed by heterogeneous catalysts. And this is also potential reaction that can be used to make biofuels. Catalytic hydrogenations are typical examples where molecular hydrogen is used to react with other chemicals, hydrocarbons, and to make, for example, methanol, to remove like hydrodeoxygenation, hydrodesulfurization, hydrodenitration, to remove components. That's done with hydrogen catalytically. Also the renewable diesel production, so these hydrotreated vegetable oils are produced with heterogeneous catalysts. So they have significance in biofuel production. Let's not go into details of this table, but this is just if you are interested. So it's quite old data, but the idea is to see what are typically the most used or produced chemicals in the world. So here are hydrocarbon fuels, sulfuric acid, ammonia, nitric acid, methanol, and so on. So these are very basic, or these bulk basic chemicals that are used in large volumes. And majority of their production involves different catalytic materials. Here is list of some these used catalysts. And this was now the benefit of heterogeneous catalysts that I mentioned a while ago. So when they are solid materials, so they are easy to separate. That's one benefit. It allows continuous operation. So basically, in large scale, you can make a fixed bed reaction. So there is fixed catalyst bed, and you can make the reactants flow through that fixed bed. So after the bed, you have products, and you feed on the other side the reactants. That would not be easily manageable with homogeneous catalysts that all would operate in the same phase. Also, these petrochemical and oil refining reactions tend to require like high temperatures, often several hundreds of degrees. So the solid materials tolerate these extreme temperatures better than the other catalytic materials. Easy separation also is coupled with easy recycling of that catalytic material. And these tend to be, it's not always the case, but one can say that these are cheaper than the homogeneous catalytic materials, at least as a rule of thumb. There are, of course, always kind of exceptions. And here are different scales of catalysis. So if we start, so there are different phenomena taking place, but this macroscopic is the reactor scale. Mesoscopic is more or less the catalyst pellet catalyst formulation size. We are talking about 10 centimeters or millimeters. And then where the actual chemistry takes place, so it's on the active sites on the catalytic materials, and then we are on a nanometer level. In between there are catalysts tend to be high surface area porous materials, so then the pores can be in between there in the micrometer level. Yeah. So in fuel production and petrochemical industry, the reactors scale is something like this, that few 1 to 2 meters in diameter, maybe easily 10 or 20 meters in height. So these are large scale equipment. Then these reactors or equipment, it's filled often with a fixed bed of catalytic materials. This being a trilobe extrudate, so it has a cross section of this trilobe shape. And here you see a regular ruler, so the dimensions are on a millimeter scale. So from 1 to 5 millimeter, let's say, this size distribution of these catalytic materials. Then there are possibilities to have several different shapes. These, for example, spheres, pellets, extrudates, wagon wheels and monoliths, etc. So these all have benefits and disadvantages and can be tailored for particular use. So these millimeter size kind of granulates, catalytic granulates, can have various shapes, and of course also size can vary. And when you go into deeper, so you can grind this into powder. Sometimes in three-phase reactions you tend or prefer to use catalyst in powder form, not in these millimeter scale granulates and extrudates. Those work better in this two-phase catalysis and fixed bed continuous operation. But then we end up this micrometer scale. So the grind powder can be on the 10-100 micrometer scale, but we are still far away from the. So this is an electron microscope image of this catalyst powder. So you'll see here the 10 micrometer scale. But then if you still zoom into one of these edges and we go to the nanometer size scale, so then we start to approach where the actual reactions are taking place. And now we have like this, like previously mentioned also, these are metal nanoparticles with some few nanometer diameter, these dark spots. So that is the active site. And then we are on a very small nanometer diameter scale. If you zoom in more, so then you start to see individual atoms, like in this graph. This I also showed you previously. But there is like quite a lot of things to tailor, starting from really the atom or molecular level all the way to this reactor level where you have the meter scale. So if you compare this, like there is a 250 times difference if you compare the size of the active site and molecules compared to the extrudates. So if you scale the extrudates as our Earth, so it would be the same as an astronaut looking for a parking place in front of supermarket from the Earth's orbit. So there is quite a big difference in understanding the scales of where the catalyst takes place. And that was just the dimensions. So also there are time scales in catalysis. So the active site bond breaking and chemical reactions are in the picosecond region. Then when we talk about the whole catalytic cycle, so we talk about the free molecule adsorbing on the surface, migrating on the surface, dissociating, doing the chemical reaction, migrating again, adsorbing, and so on. This is a millisecond. And if you have these extrudates, this millimeter scale, so the diffusion from the outer surface to the inner pores and surface can take seconds to minutes. Then talking about those reactor time scales, so when the molecules flow through the catalyst bed, so we can talk about seconds. And this is the other extreme, that talking about catalyst poisons, so they stick on the solid surface and never leave. So that's the one function how the catalyst poisons and deactivation takes place. And the catalyst lifetime from start till death, it can be, like I mentioned, few seconds in cracking catalysts and several years in some of these oil refining like catalysts, that those reactors are charged and run for few years, and then the catalyst is replaced. So here I wrote just to myself a task. Of course, this is something that you can also do. So after this, so it might be, or if you take a look at the course textbook and you search the document with the word catalyst or catalysis, so you can find easily 20, 30 different catalytic materials at least there that are used in the biofuel production processes. Few words about or maybe we'll have now a 15-minute break, because yeah, so let's continue after 15 minutes with this topic. Okay, we'll move on. So few slides regarding catalyst materials. So like mentioned, there are hundreds of or thousands of different catalysts in industrial use, and one can group those based on their functionalities or properties. And this graph is showing that quite many industrial catalysts are metals. Some are oxide materials like aluminum oxide or chromium, vanadium oxide, and so on. Sulfide-based catalysts are used in sulfur removal, for example, and then acids and bases are also typical catalytic materials. And these can be, of course, like normal mineral acids like sulfuric acid, hydrochloric acid, or then these can be also solid materials which have acidic or basic properties. If we talk about heterogeneous catalysis or catalysts, so these often are porous materials, meaning that there are tiny pores that increases the surface area. And you remember that heterogeneous catalysis is about surface reactions. So the larger the surface, the higher the rate of the reaction. So therefore we tend to use materials which have very high surface area. And very often this so-called support material is the porous material with large surface area, like illustrated in this graph. Then the catalytic metal or catalytic material, it can be metal or oxide, or for example that base or acid site. So those are distributed on the surface of the support material. So there are these tiny dots or areas which are the catalytically active parts. Then one can add additional so-called promoters or materials that make the catalyst work better, tolerate higher temperatures, resist deactivation, and so on. So this graph here comprises these different aspects of a proper working catalyst. So there are the active components, so those make the chemistry happen. Then there is the support, which provides mechanical stability, the high surface area, as an example. Then additional chemicals or features called promoters that somehow improve the performance of the catalyst. When we talk about making of these industrial scale catalytic materials, these millimeter or centimeter scale materials, so there are many parameters or things to consider. This is just a list of some, and I will not go many of these in detail, since I had three today. I had from old materials over 300 slides, and I had to cut or delete a lot of this material. So just a list, some. So I will not go into details, but this is a periodic table of elements, and although it's here is just listed that what elements can work as catalytic, what elements can typically catalyze reactions, what are used as supports, what are promoters, and which are poisons for these type of catalysts. This is only a little bit repetition, but basically the catalytic function or the active component, so it depends on the reaction that you want to do. So you have to select it out from all these possibilities and the different chemistries. So you have to select which one works for your reaction best. If you are doing hydrogenation, or if you are doing oxidations or some other reactions. So there are certain materials that work and most do not. And also among from those which work, so some work better, some work a little bit worse. And then it's matter of optimizing the composition, all these promoters, the support material and other properties, trying to make an optimum mixture for that particular reaction that you want to carry out. This is just an example of an ammonia, industrial ammonia catalyst. So there you'll see the bulk composition of this BASF catalyst, and you notice that there is iron potassium, aluminium, calcium, and oxygen, like elemental composition. Some of them, like iron, is clearly, I would say, the active component. Okay, here it says that, yeah, iron is the active metal or metallic component. Then this aluminium and oxygen comes from the probably alumina support, so that gives the support, and potassium and calcium, not sure, or potassium, at least I have written that it increases activity. That means that it's a promoter that improves the performance of the catalyst. But these are like not complicated mixtures in that sense. Here is again collected some example of promoters, and you'll see here catalyst and the promoter, and here an explanation of what it does. And here is like it's poisoning certain sites, it's increasing acidity, improving stability, increases oxidation reaction, slows down sintering, and so on. So it has several functions. I mean, these are added in small quantities, but they notably improve the performance. There was a word like called catalyst poison. Poison are often these elements or chemicals that stick strongly on the catalyst surface and are there, and you cannot remove them. So they like cover the active surface area. So there is, after poisoning, there is less active surface area, there is less activity, and the catalyst doesn't work so well anymore. So this is undesired phenomena, and the poisons can come, for example, from the feed. So biomass tends to have, like crude oil, tends to have lots of different molecules and atoms and inorganics and organics involved. So some of them can act as a poisons. So if that's a big problem, you might need a purification step for that feed to remove the poisons, the unwanted matter. Poison can also come from side reactions taking place on the catalyst. This is not that uncommon, that there is the main reaction that you want, and then there are several side reactions, and some of those can cause catalyst poisoning, or some of them can cause just side products that you don't want. And also, of course, typically some tiny metal particles and so on can come from or some materials can dissolve out from the hardware, from the process equipment. But these are just few alternatives for what causes the inevitable catalyst deactivation. Support materials, so those that provide the mechanical strength and high surface area, there are several alternatives. This is the list of most common ones. So activated carbon, zeolites, silica, clays, alumina, and is kieselguhr. It's also some kind of type of silica material. But why I put this here mainly is that this is the typical surface area of catalytic materials. So if you take 1 gram of activated carbon, it can have surface area of 1,500 square meters. So tablespoon of activated carbon has like 1,500 square meters of surface. So this is one reason why the catalytic materials are so powerful or well functioning, is that they have huge amount of surface area there. So there are lots of sites where the chemical reactions can happen. Here is maybe more longer list of different type of support materials, but here's also like acidic and basic neutral support materials. Quite many of these you can find if you go through the course book and see what type of catalysts are used. So it's very often written in such a way that there is the active metal or active component and then slash the support. So this could be basic, could be like nickel, magnesium, or here the neutral could be some platinum or palladium and so on, and then the support material is written after that. So here I think here are different types of aluminium oxides, or called alumina. So I will not go into details, but also notice here that this large surface area, that's the key point. We are dealing with surface reactions. We have to have lots of surface so that the catalyst is active. Or activated carbons are commonly used as surface support materials, and they also tend to have very high surface area. Activated carbons are often quite neutral, so they don't tend to have acidic or basic properties as many other support materials have. The newcomers might be carbon nanotubes, but I will not say more on those, but can act as a support material. So regarding these support materials, said already, but it provides the rigidity and the support where the active sites can be deposited. Typical materials used in this are aluminium oxide, silica, activated carbon, titania, molecular sieves. These are the so-called zeolites. That's the you'll see soon or next what they are about. And some acid-base catalysis can happen also on the surface, and it can be that like in certain zeolites, so it's enough that the support of the zeolite has this acidity that actually also is the catalytically active function. So it doesn't always have to have some metals or some extra materials added on the support. When we have those tiny metal particles, which is very common in biofuel or fuel processing catalysts, so we call them supported metal catalysts. So the support also prevents sintering, and this graph here illustrates sintering. So when you have these tiny nano size clusters or metal particles, so they tend to stick to each other and form these larger and larger particles, and this, when the tiny particles emerge and disappear and form larger clusters, so this is called sintering. And on a support, if you have lots of material close to each other and you heat it up to a few hundreds of degrees, so these tiny particles can migrate and merge, it's called sintering, and forming larger particles. And what happens in this process is that you lose the surface area. So 10 smaller particles has much higher surface area than the same material merge into one big ball or sphere of that material. And the support one function is that it prevents also this. This is one cores for deactivation, the sintering. If the active phase or the active metal particles cluster, sinter together, they lose surface area and the catalyst loses the activity. These metal catalysts come in different shapes and forms, and again I have skipped majority of those, but there are different categories: massive metals, blacks, powders, skeletal metals, supported metals, and mixed metals. And I will skip more or less all of these. We have talked quite a lot about supported metals, and you should have already an idea what those are. But here is some collection of, I have mentioned that hydrogenations or reduction reactions are often in fuel production important. We'll encounter those later on. So here's for certain reactions listed catalytically active metals. These are often this, not always, but quite often are these noble metals, which tend to be rather expensive. And one reason of using these supported metal particles is that if you have very expensive metals, so you probably tend to optimize the surface area, and that can be optimized by making nanoparticles, nanoclusters and spreading them on the support. There you can get from 1 gram of material the maximum amount of surface area. These additives that can be added, like when we have mixed metals. So this I mentioned this promoter concept, so that it improves the performance or optimizes the performance. So there is the active catalytic metal, but once you introduce some other ingredients, it might work even better. Here are just examples of those combinations. I will not go through in detail. Zeolites can be found in nature. So these are highly porous hydrated aluminosilicate materials. So they have very fine, well-defined structures, and these are the natural zeolites and synthetic zeolites are used, for example, in detergents and adsorbing material, and some economically important area is also catalyst applications. There are many different zeolite materials or these 3D structures available. Here is one which is used in fuel production. It is ZSM5. You'll notice this name also in the course textbook. So zeolites they are this kind of, one name is molecular sieves. So they have very tiny channels, very tiny holes with very well-defined structure. And that can actually help to catalyze reactions and work in fuel production as well. Here are some common names for different zeolites. So mordanite, fayazite, X and Y, ZSM, different ones, zeolite A, and so on. So they have this channel structure, and channel width or diameter can vary. These are some properties of different zeolites, so I will not go into details. This picture shows a bit like this, how this these are constructed. So there are like these channels and spores that are the key to the how the zeolites work, or the molecular sieves. So we talk about size and shape selectivity. In the next slide, it's defined how it works. This zeolite has potential for being very strong acids. So this can be comparable to sulfuric acid and hydrochloric acid. So we want to use these for hydrolysis of molecules, polymers and such. But these are liquids, so these are difficult to handle and separate. So once we start to use these acidic zeolites, so we have similar strong acidity, but we have it in a solid material. So that's a very useful feature for industrial catalysis. These also are these inorganic materials that are very tolerant to high temperatures. And the structure is crystalline, so it's very well defined throughout the material. So it's not like in amorphous materials that the structure vary. So these are like organized, well-structured materials. And the reaction selectivity, there is like called shape selectivity. So different versions of it are reactant, product, and restricted transition state selectivity. The reactant selectivity is very simple, that once these well-defined pores exist throughout the material, so only smaller than the pore diameter molecules can enter the catalyst and undergo reactions. So this is kind of also the molecular sieve action of zeolites. This can be used as drying agents in organic chemistry. So you can, for example, remove water from organic solvents so that the holes are tailored so that they fit water molecules, but they don't fit the larger organic molecules. So then from that liquid, water molecules tend to enter the pores, and once you filter the solid material out, so you have dried or you have removed water from that matrix. The other opposite to reactant selectivity is product selectivity, and it's the same thing that only products that are big enough can exit the structure. So that's the kind of selectivity. And transition state selectivity refers to that chemical reactions go through a transition state, and it usually has a certain geometry, well organized geometry. And if the geometry is not possible inside the zeolite, so such kind of reactions will not take place. So it can help to selectively do things. Enough of acid, but like if we talk about solid acids and in some, so then we usually find those very strong solid acids among zeolites and synthetic zeolites, maybe not so much of a natural ones. But because acidity catalyzes many fuel reactions, so these zeolites are quite, or the most of them have been developed for petrochemical and oil refining industry. You can also incorporate metals in zeolites. So then the zeolite framework would be like a support, and there would in addition come catalytically active metals, so on. That's also used as a possibility. This representation here, like if we have the MCM41, it's a type of molecular sieve or type of mesoporous zeolitic material. So MCM41 is the zeolite, and then if we have added metals, so the catalyst looks like sodium MCM41, platinum MCM41, and so on. It's just a way of writing this. You'll see some of these appear also in the course textbook. The surface area readings are nearly as high as with best activated carbons. So this is it comes from the well-defined crystalline structures and these micro and mesoporous channels that increase a lot surface area. Then there was type of catalytic materials that are oxides, and oxides are usually chemically that there is a metal and then it has oxidized, so it contains, let's say, usually oxygen in that chemical formula. So many oxides are used or catalyze reactions. So there can be single oxides or mixtures of metals and their oxides. We can also use supports and coat and add there these oxide sites and so on. Then last, or maybe nearly last, there is also this basic catalysis. Certain reactions are catalyzed by base. And very cheap and common is sodium hydroxide, but this is liquid material, so it's not really heterogeneous. It's very difficult to separate. So one also has these solid basic materials that can be utilized. So here's a list of typical ones, so that have basic properties. So some of these are also used in biofuel processes. Sulfides are also in connection to fuel production important type of catalysts. These are not otherwise used very much, but these are used in sulfur hydrodesulfurization. So there is again this hydrogen and then D something, so removal of sulfur with hydrogen, and it requires this special sulfide type catalyst, and these are used to remove the natural sulfur from crude oil so that we will not get any more these sulfur oxide emissions when we run combustion engines or diesel engines. So this is the technique to remove sulfur, and it can also be used to improve the biofuel properties in some cases. And of course, there are lots of other possibilities for let's say different innovative ways to how to incorporate catalytic activity into materials and utilize it for let's say making of biofuels. So ionic liquids have been used to, for example, to dissolve and digest these lignocellulosic materials. They can also do many other things, but these are quite expensive materials. So one can, in order to ease the recovery and reuse of expensive materials, one can deposit those on a support. So it's kind of a hybrid heterogeneous catalyst with the similar support and ionic liquids attached to it. One important thing which is heterogeneous catalysis, and it's also used in biofuel, like ethanol production, for example, is immobilized enzymes. So if you immobilize the enzymes on some kind of support or solid matrix, so it again enables the good things of enzymes catalyzing the ethanol production, but it helps to recover or remove the enzymes from the mixture. And the same immobilization can be done with other types of catalyst as well. But there, the immobilization comes from the fact that we want from soluble materials or homogeneous catalysts get the easy separation of heterogeneous catalysts. So this enables that. So here was a long list of different types of catalysts and supports and how they function and so on. But it is the kind of a short introduction or first touch to the catalysis, but it's very essential for making these biofuels. So more or less most of the reactions and processes that we go through are catalyzed with different types of catalysts. So one should not forget that without the catalyst, the process would not work, or it would not be possible simply by increasing the temperature or something, that it needs that catalyst for proper functioning. So therefore I added here that these also from all categories, some catalysts are used for biofuel production.